Hello everybody, my name is GrabBG and today we're going to continue to check out Hog. Hog is a language we've been working on for the past little while, I guess. We haven't yet done anything too big, but we've developed like a library behind generating Java bytecode, so now we can actually use that to make our language and generate the bytecode. So currently, what our program does, and if we open it up in the editor, is that it just currently generates an empty program that just does nothing right now. So we have the main function, right? And we only really have one instruction, that's the return instruction. We just return nothing, right? So how about to kick things off, we actually get a thing working for actually printing something to the standard out, like for example hello world. So a hello world we've actually made in Java before, and that's actually located back in Javers. Javers is actually the library, and then Hog is actually a sub module inside of that entire workspace, right? So I think we have something like temp.java. Let's see. No, it's not temp.java. It was in JaversLib, I think, JaversLib. The example, which was, no, not here, probably in the Java disassembler, right? So, yeah, example. So in here we have a thing called hello world class, .class, and hello world.java. So hello world.java generates hello world.class, right? So we can actually check out what it disassembles back to by doing cargo run --bin jdis on hello world.class. So it compiles the stuff and we get this, right? So a few instructions. We're actually probably gonna, you probably don't see a lot, but in here these are the instructions. So the instructions we're aiming for are the exact same. Essentially, we want to get static 2, which get static 2 is inside of the constant pool. Which one? This one, right? So we want, what they do is they get system out and push to the stack, right? To the operator stack. Then we want to push hello world to the stack and invoke virtual for. The invoke virtual is because print stream, I think, is some sort of like interface, maybe, not sure, don't quote me on that, but Java.io print stream, we're actually calling to the print stream println, which is a method inside of system out. So basically, if we kind of like go back a little bit, we're getting we're pushing system out to the stack, right? We're then pushing hello world to the stack, and then we're calling to system out println, right? Like this, and then we return, right? So that's what we're going to aim for. So we would probably need to do a little bit of like a little bit of extra stuff. So we again want to return like normal, right? So then we also want to get use the instruction for what was it? Can I, yeah, let me just open up the source code for the instructions, right? So code.rs. So in here we actually have some instructions, and we're going to do what? We're going to first get static. And what kind of static are we gonna get? So we want to actually get the another function called right. So we want to, no, not the method, actually it was what it was right. So we want to get system out, right, which requires us to create a field ref, because out is a field inside of system, right? System, and then we want to get out, which is a field inside of there. So we're going to do something like outref equal to body constants create field ref, And what kind of field do we want to create? What kind of reference do we want to create? So in here it says that we want to get Java lang system, and the thing we want to get from it is the out field, which the out field is of type this, right? That's the type. So let's actually put it there, right? So that's the outref. And we also need one extra thing, which is the print1, right? So for that we actually need a method ref, I think, for what I remember. So that's a field, that's a method ref, yeah, method ref. So we just need to create a method ref to print stream print1. So the way we do that is just print1 equal to body constants create method ref, and that method ref is actually going to reference Java IO print stream, and the actual so the actual thing we want to get from print stream is print1, right? And we also want to get its actual definition. So the definition is it's a void function. That's what the V stands for, and it accepts a string, right? So it accepts a string and it's a void function. And then what we can do is actually get static for the outref. I think that's ID. We want to get the field for the outref. That's actually probably I don't really remember how to make it bigger and kind of zoom in, but let's just do instruction. We want to get the static thing for the static reference to the system out. Push that onto the stack, right? You can imagine that that's pushed onto the stack, and then we want to push hello world. So the way you push hello world, for what I remember, was an I load. Oh no, it was an A load, right? I think it was an A load. Or what? I'm not really sure. Oh, maybe it was like, give me a sec. So in here we have push hello world. So we can actually look into the source code, right? So edit source main.rs. Now we want to do /javaslib source, and we want to look at how it's deserialized. And in here we should probably have something like implementation instruction here. Yep. Or it's probably serialize. Yeah, we probably want to look at serialize where we actually print it, I think. So serialize, we want to check out where we have push. So it's not here. Maybe it was what? It was logging. Do I have something like that? Yeah, we have logged it. Alright, so push. Which instruction is push? Oh, it's LDC. Okay. So it makes sense. So we want to load a constant from the constant pool. And which constant do we want to load? Well, we want to load our string. So our string is gonna be a string ref, I guess hello world. It's gonna be equal to body constants create string. Was it? I think it was something similar. So it was maybe pools.rs, maybe in there it's actually kind of set. So create string. Okay, that's just create string. It's inside of the constant pool. Okay, so we just create string. So let's create string, and we want to create hello world. So that's what we want to print to the standard out, right? So we're getting hello world. That's what we're loading. And then we shouldn't forget to also probably push code to system out println, right? So what we want to do is call the invoke method to invoke virtual, right? So we want to invoke virtual, and that virtual method is actually going to be called print1, right? So we're looking to call system out println on the hello world string. So it's probably not gonna compile from the first it's not gonna compile right away, but that's fine. So let's go to probably we can just go to hog, right? So cargo run, and what should happen is the system cannot find the path specified. So what is it? It's probably yeah. So I think I had something like cargo run -bin hog, and it has to be in this library. So we wrote to output class, right? And then we can actually run our disassembler on that output class to see its disassembly. And what you see is that we have get static 19, push hello world, and then invoke virtual 25. So 25 is going to be our println, right? So 25 is our println. Hello world is our string, and 19 is system, if we can find it, system out. Right? That's what we want. So the question is, can we now run this? Well, we can try, right? So we can run the Java virtual machine on output. And what do you get? Right, we get hello world. All right, so now that we've got this out of the way, I mean, you can with just this, you can probably do even more cool things. Like, for example, let's actually print 2 strings at once. Let's have hello world and foobar, right? Classic example, foobar, right? So it's gonna be the exact same thing, except that now we're going to also load foobar, right? That's it. So if we write this and just go back and generate our code, cargo run hog, and we go to output and we run it, we should get hello world and foobar, right? So that's cool and all, but a language itself by definition should take in some sort of input and then output something, right? By definition. So now we have the output part done, but we don't really have the input part, do we? So we're going to do something a little bit like I have like a little idea for how the syntax is gonna look like. So let's actually write a hello world, right? So how is our syntax gonna look like? Syntax, again, doesn't really matter too much. This is important, but essentially, if we open up our examples, we can write a hello world. And since our language is hog, I feel like an extension of .hog is fine. So the way I imagine it is a language that looks something like this, right? So you can get externals, right? So the externals, why do we start here? So if we want to get like into the little parts of it, I don't think we currently need external because we're not going to be doing anything too advanced with this. I feel like I don't think we're going to get into that just today, but the syntax that I want is to generate some sort of, get the input file, hello world.hog, and that hello world.hog, maybe let's actually not start with hello world because it's a little bit more like, it is gonna take a little bit more time. So how about we start with what every language does, right? Every single language, I think, starts with this, which is sum, right? So you define a sum function, right? Sum, which takes in an integer, and then it takes in, well, yes, it's an integer, it doesn't matter. So maybe it's, yeah, let's take in an integer, then it takes in another integer, and then it can also return an integer, right? And the example is that now you can do a plus b, and we can compile this, and what we want to get at the end is a class file called sum.class, which in and of itself is going to contain these like this function, and that function is going to be static, right? It's going to be static, and we should be able to call it from an external program. So first of all, I am not quite sure how like including worked in Java, so let's actually first start off with that. Let's just clean real quick. So let's make a temporary directory, and let's create a file like hello.java and sum.java. Yes. So if we open up sum.java, maybe through our editor here, temp sum.java, right? So the standard stuff, public class sum, and then we're going to have a public static integer function called sum, which takes in an integer a, an integer b, and it returns an integer, of course, and it just sums it. Right, like this. And then we're going to do, let's actually cd to temp. And then from hello Java, we're going to do public class hello, public static void main string args, like so. And can I theoretically do system out println, or how does let me actually look up system out println, because I think they should have it in here. Can we we can just convert it to string, so, or it can just print it itself. So we want to just do sum 5 6, maybe we can even abstract them away into two variables, is equal to 4, and essentially that's sum, and that's going to be a, yes, sum of a, and then a comma, and then b, and then that, and then that results in what? In what is the result of that, right? So that's what we want to do. So let's actually compile sum. Classes name are only accepted if notation specifically requires it. Maybe let's actually do something like sum.java, sum.java, so it's like a capital M, and maybe we can also move the hello Java to hello.java, like this. So let's edit hello.java, and that's capital H, and that's gonna be also S and S, and then sum.java is actually gonna have a capital, like this. So let's try to compile it. Sum.java, public class sum is public, should be declared in a file called, oh wait, what? Yeah, right. So what? Hold on a second. What? Something isn't quite right here. What happened? Move hello.java to hello.java. Right, so sum.java. Alright, that's compiled. And let's compile hello.java. So it's missing something. And what does it miss? So it's missing, I guess, what? So first of all, I don't think it's something's wrong with my quotes here. So it's this. Yep. That's fine. It's missing some, right? So let's try to actually import it. Import in Java, not script, but Java. Okay. Import package.java class. Can I do something like import sum.sum? Sum.sum. Can I do that? I probably can. Alright, so error closing bracket expected. Why? That's weird. So wait, we can compile hello.java together. Expected semicolon. Yep, I forgot the semicolon. Sorry. So now what's the problem? Error expected that. Why did it expect that? That's weird, right? So maybe it doesn't recognize sum itself. Maybe, yeah. So let's kind of do include in Java. I'm sorry I didn't prepare this, but import static package class methods. Import static sum. Maybe it's sum ::sum. Not sure. Maybe it's sum.sum. Okay. So what do we want? Okay, so we don't want to do that. So Java packages and APIs. So we have a name, class, utility, whatever. So that's our hierarchy, right? So that's root package mypack. Sure. So actually it's package temp, right? So that's package temp because it's part of temp, and then sum.class is package temp as well. So now they should probably share it. Give me a second. They should probably share it. So that should be temp.sum.sum. So that is now what? It's still not working. Expected semicolon here. Maybe we just print it. So wait. So what's the issue? Right, so sum actually accepts 2 arguments, let's say MD. Probably that. Nope, doesn't do that. Doesn't do that at all. So can I do something like line result equal to sum a and b, or sum result? Can I do that? I can. So symbol variable sum, symbol sum. Cannot find symbol sum. So can I now link it with sum? Gotcha. Class sum is public, should be declared instead of sum. Okay. If Java wants to play it this way, I will just do it with a lowercase one. So static import only from classes and interfaces. So can I just do import? Nope. Java. So sum.class, that's sum. I think I changed it. Variable sum, cannot find symbol, sum. So is that temp sum. I'm sorry I'm taking this long to do this. It's just Java being Java, and I guess that's also sum. Maybe it's just this. So sum.sum class location class. Can I do this instead? So that should be it, right? And that compiles, right? What if we don't provide it? It cannot find it, so it has to be able to link it like this. And should Java hello Java, should Java, I guess, Java hello. Java like no class definition for temp hello, wrong name, hello. Okay, and just sum, wrong name, still. No class definition found, so what's the issue here? Public static void main string args, right? So we generate some class files. Let's actually remove some.class and remove hello.class. Hello, for double hello.class, and we generate them. So that's hello.java and some.java. I generated both of them. So that's Java. Can I do it on the current directory? Cannot find the main class. Maybe it's hello without class. Temp hello, no class definition found. Wrong name, hello. Caused by Java long temp / hello, wrong name, hello. Okay, so maybe we don't do package sum, we just import it like this. That could be the issue, I'm not sure. So temp sum, yes, so now we need to also load sum. Okay, so exception in main thread, Java no class definition found for temp / sum. It is though. So okay, give me a second, just a quick one. Right, so we want to import sum from the sum file, some Java. No need to make it temp. And now let's regenerate them. Expected semicolon, accepted dot. Okay, maybe it's package dot. So that's essentially hello world dot Java. Import package dot sum. Identifier, missing identifier. Is it string? Maybe it's static. Still not. Import static sum. Still nothing. So hierarchy. Can I actually see the hierarchy? Save this file and then compile to the package. Aha, okay, that makes sense to a certain degree. So we want to import temp.dat, and where did sum go? So that's here. We still want to do package temp, and then when we compile, in here it says to use the -d option to out.class javc. Maybe, oh, it has to be like, we have to link with everything. Hello Java and some.java. Okay, so now that compiled into something, and Java temp could not, maybe I have to do, yeah, Java temp dot main. Java temp hello main. Class not found. Wow. So wait. So I had to also do that in the main function, is what you're saying? Wow, that's. I mean, sure. That's why we like stuff like. Hello. Yep. So now it works, right? So that was what I wanted to prove, that we can import stuff between different packages. So within a certain package, can we do something like hello? Yes. We can. Can we do this directly? That's hello Java. And maybe now we can run it with hello. Still works. So if I change the source code now for some Java, right, and I do +5, for example, that should be +5. So before it was 9, and now if I do Java C specifically on some.class, some.java, and I run it, dem.hello, it's 9. So it has to relink it somehow. No source files. Hello.java, I guess hello.java, and now Java, I guess Java temp hello. Still 9. So how does that actually work under the hood? It's interesting. Maybe we want to be able to test it. How about we actually do something like, okay, Java C hello Java C this -d this on hello.java and some.class. Can I do that? Java C, any help? Release proc processor profile release source. Can I do add modules? Directory enable this no warn proc profile as link with class file Java. Class file with Java files. Okay. Because it's compiled with Java files, assuming that. So, right. So -d here some.class. Right. I haven't recompiled the Java file. Can I theoretically now run Java hello? Java temp.hello. Yeah, and now it updates. So I have to actually update it myself. And what is inside of temp? Temp is not a directory. So temp hello. So temp just stores them. Okay, that's fine. That's actually fairly reasonable. So the way it handles things, for what I can understand right now, is that it puts all of the stuff inside of this directory called temp, right? Because it thought it was under a package called temp, it put them in this directory, right? And once I ran that directory using the Java virtual machine, and I specified I want to run it with temp and hello, it relinked it and redid the stuff. Alright, that makes sense. So the way we're going to set up that testing environment now that we know at least how it works, is that now we're gonna do Java assembler. Now we're gonna go to hog here, and we're going to do something like make directory for the test sum, right? So we can do going to test sum. So the testing environment for test sum is gonna be our hello.java, which is going to have the package called tests, I guess. Yeah, we can just call it test. And then that's public class hello, public static void main string args, right, like this. And we're going to do something like, we're going to import from test, we're going to import sum, and we're going to have a equal to 6, b equal to 4, and we're going to do sum.sum of a and b, and we're going to log that. So the way we're going to log that is actually probably going to be system out ln like this. So that's essentially going to be a, so sum of this a, this b, closing brackets, and of course is equal to this result equal to that. All right, so that's res, and that's essentially, yeah, that's it. So that's gonna be our testing environment, and we're going to do now going to do probably back and back again, remove, probably keep this for right now, going to hog, and start by first generating some stuff. So where are we going to put our stuff, right? Where are we going to do all this stuff? So we're going to be first trying to generate a file given some sort of input, right? So the input we're going to currently have is a bunch of functions, so we can imagine it, right? So let's actually go into the editor and actually start working on hog. So the way you can imagine it, right, is when you're building a programming language, there's a few steps, right? So you have the front end of the language, which is kind of like the syntax and also probably the parsing stage. So the front end is responsible for taking that string, input string, and translating it to something that's more efficient for the computer to use. So in this case, right, we can take, you can imagine it as like, if you know assembly, right? So assembly is just some strings that you take in, the front end is just reading those strings, parsing them into the little instruction parts. And then what happens is, inside of the backend, that optimized, right, input gets turned into an output that we can view. So in our case, we've kind of done the backend, in quotes, right? We're generating the stuff, but we don't really like have a front end yet, which is actually fine. So currently, I don't think starting, like, we've started from the end, right? We're starting from the back end. The back end generates those that output. And right now we should probably focus on actually taking like a function, a singular function, and making something out of it, right? Taking that singular function, which I'm going to have to define, or maybe even a set of functions with their respective instructions, and turning it into something we can parse. So I want to see exactly how stuff like sum compiles. So how about we actually do that? Since we have a disassembler, it's probably going to be fairly straightforward. I'm going to run this on let me just kind of get that. So we're going to run the disassembler on output, or probably temporary sum build class. Could go run, right? So could go run. We have an unknown opcode, so that's why we should open up the manual for Oracle. So Oracle Java Virtual Machine Specification. Again, I'm going to have this in the description for anyone that wants to check it out. But we've done this in the past episodes. We've explored this and implemented like a basic library that actually handles this stuff. So the first thing we should check out probably is the instructions. So instructions, I think, were just for type checking. Instructions here. So we're looking for this, right? So what do we want? We just have the opcode, right? We have the opcode 08. and we want to turn that opcode into an instruction. So what do? We just search up 0x8 and we probably closing bracket. And what is that? That's iconst underscore. So why would that matter? So inside of our sum implementation, right, let's actually VS with it. So inside of our sum implementation, we have that's not what I wanted. We have this, right? We add another 5, which is a constant. So it uses some sort of constants to add to the stack before adding them together, right? So in our case, we don't really want that. Let's actually compile it and remove that like unnecessary thing. So temp recompile somewhat Java, grab C, somewhat Java, and go back. And this is sum once again. And what do we get? So we have a few instructions. The first one is iload, and the count is 0. So iload instruction should do what? Well, we currently don't exactly know what it does, but from what we know here, it's kind of the I implies we're loading an integer from a local variable. And local variables are stored in a stack. Well, not a stack, but like an extra virtual space where we have them. So the locals, right? The locals actually get loaded with these arguments we take, the two integers, and then those are put into the locals, right? We take in the first argument, the second argument, and we add them and return, right? So how about we actually do the bare minimum, like the bare minimum to generate a similar file, right? So what do we need for that? So we first need to kind of understand what we're making, right? We want to have something like an instruction which is gonna kind of collide with this. So maybe we'll just do code like so, and we do code instruction. So because alright, so imports are a little bit weird in the case that they're gonna collide with this. So maybe we can just do something like this to differentiate them. So we want to define actually an instruction, right? An instruction. What is an instruction? An instruction is just a basic operation that should be done by our computer, right? And in our case, right, we want to have a few instructions. So the first one is an instruction which would push I guess probably load the argument arg, or I don't know how to really do this. I can't really visualize it right now. So we have some sort of instructions here, right, for the backend instructions, which right, let's actually divide the language into the compiler itself into separate sections. So here you have the lexer. Lexer takes that string that you take read from the file, and it transforms it into tokens. Those tokens get fed into the parser, which the parser translates into something more readable, right? So it translates them into, for example, if you have an expression like, for example, a plus b plus times c, right? The way that the parser would take that, most parsers would just take that a plus b, right? And that's gonna be that's b plus d, right? It's gonna parse that b plus d, and that's gonna be one part of the string, the tree. That's the right side. The left side is gonna be a, and the plus sign is gonna be the actual root. So you have plus A and B times D, which in and of itself is another tree. So I won't get into the details. You see what I mean later on. So then that build has to be somehow turned into our assembler / compiler, depending on your idea. So on what you're making. So in our case, it's some sort of compiler to Java bytecode, but it basically takes your build, the things you have already, and it turns them into something that can be read from the computer, like for example Java bytecode, in this case from the Java virtual machine. But sometimes there's actually there's extra steps here, and those steps can vary. So you can actually have different layers, right? For example, LLVM, there's a lot of different layers where you have the AR, the IR, I mean, like if you've worked with LLVM, you probably know what I'm talking about, right? It's not just parser assembler, right? You usually don't do that. So what we want to have, in our case, we don't really need anything too fancy, right? I feel like just a really basic idea of what we want is all we really need. So, and for a sum function, right? I don't think we need this step. In our case, we don't need it. We can just take it directly, right? So the instructions that we need for a sum are probably return. That's kind of important. And maybe sum is a little bit more complicated instruction. So how about you actually have something like, instead of implementing sum, let's actually implement something that just returns an integer, right? And we know how to return an integer because that's just the instruction for iret, right? You push the integer on the stack and then just call iret. And we can check this out here. So return is what we need currently, and we want to return what? Some sort of value. Maybe we do make it a little bit shorter. So what is a value? Well, a value is, for right now, we can actually define value as just being a constant integer. That's just an i32, I guess. And that's gonna be essentially it. So what do we do now? Well, let's actually define our structure. So that's gonna be our build, right? We want to have a first of all, let's actually define a function, right? A function is actually just something that has a body of instructions, right? So for example, this here, what are the instructions that are going to be that we're going to have? Well, we're going to have one that's called for return, and inside of it we're going to have the instruction for like summing them, right? For example, if you had more of them, like for example, if you had print hello, print foo, those are 1, 2, 3 instructions, right? 3 instructions. And that's basically the body. The body is just a bunch of stuff that we can take and transform into other stuff. So now that we have that, let's actually try to compile a function, right? So let's actually define a function. Let return integer be equal to a function with a body that's equal to a vector of, well, it's a vector of instructions, and the instruction we want is an instruction for return, and we're returning a value called an integer, and let's return, for example, I don't know, 69, right? 20. So we can now take this retint and let's try to compile it, right? let's try to compile it. So how would you compile it? Well, first of all, here we initialize the class, right? Here we initialize a main function. We no longer need to initialize a main function, right? But we can now take this function that we had, retint, which actually we can define even further down here, and we can actually convert it into some actual useful instructions. So that's going to be essentially for instruction in the return integer body iterator, right? Iterate over all the instructions, and then we can match the instruction to check what it is. And in case it's a return, instruction return, we have some sort of value that we want to return. And what do we do with that? Well, we can again match the value and just be like, okay, well, it's an integer. We only really have one. And how do we translate that? So that's really simple, I think. First of all, let's actually create the function body. That's essentially going to be a mutable block equal to a code block default. Or you create a block. Then, looking at this, right, so then we can take the block that we created for the function and translate it into something like this. So we want to push even more instructions into it, and at the end, so in here we have to do this return integer, and in here we want to do body create methods main, in this case return integer, right? What flags does it have? Well, it's just public and static. And we now need to define what I like to call a contract. Basically, what is the signature of the function, right? What's the signature of the function? So, for what I can remember, the signature for a basic function that takes 0 parameters and returns just an integer is just this, right? And that's gonna be code, right? So that's gonna be code, which code is gonna be code equal to block create attribute code block. So right, and that's basically it. So we've generated a function, right? So let's actually try running it. This generates a function. Okay, let's actually go to hog and then run it. And we still have a few stuff to do. So first of all, we should use javaslib act public and static. Public act static, like this. That's clear, and run. We also want a code block. We also want variant or associated return. Yeah, it's not capital return. I think I made it just like lowercase e, like this. Method not found in code block. Create attributes. What was it? Body create attribute. Maybe, yeah. Body create attribute. Right. And we get this, right? We haven't implemented right now, returning an integer. So the way you return an integer is you first load a constant integer, and then you return it, right? So in our case, we need to load the value and then call to iret. So we're looking for a function that can return, it can load us a constant integer. So push the int constant onto the operand stack. Push int constant. So maybe it was iret. Yeah, I const. Wait, what? That's weird, right? So what instruction loaded constants? Let's actually check it out. Yeah, let's actually just check it out. We have a disassembler. I don't know why we're not using it. Let's go into temp and let's make a file like temp java, and instead of temp java, let's just have something like public class temp, yes, test, public static int a return 9. temp.java into temp the test.java, right? And we want to compile that. javac temp test.java. All right, that's test completed. And if we run our disassembler on the temporary test.class, we have an opcode of 0x10. So that's interesting. What is 0x10? Byte push byte, right? That's interesting. So we haven't implemented that yet. Let's actually do that. So the workflow for this is that we modify the javaslib as we implement more stuff. Right. So pushing a byte seems exactly what we want, but it's too much of an optimization, right? We want to push an integer, a whole integer. Push. Maybe something like iPush. It pushes a byte. This pushes a byte. Byte push. Byte push. Byte push. Short push. And then, so you can push a short. What? That's weird. So you don't have an integer push. Swap. Really? I store. I push. So it doesn't have it. That's weird. So why? Wait. So let me explain a little bit why I'm so confused. So the Java compiler optimized our code and turned that 10 into a byte, a single byte. The Java virtual machine can load, right? So my question is, since they don't seem to have an instruction for pushing an integer. They have a one for pushing a byte and pushing a short, but they don't have one for pushing an integer. That's a little bit weird. So what's up with that? Well, let's see. Right, so we can edit what test.java, and let's actually return like a value that's insanely big, or I guess too big for a short. So that's 2 bytes. 4 byte. That was 2 bytes. That's 4 bytes, and that should be enough for a integer, but not enough for a short, right? What happens when you do that, right? javac temp test.java. All right, let's return on the assembler. So JDIS 0x02, huh? I const m1. Wow, okay. Push an integer. So each of the family instructions by push for the consecutive value I, except that operand I is implicit. So what does it actually do? I'm a little bit confused, right? So m1 is -1. Yeah, no, that makes sense. So, oh, okay, so it's another optimization. So, if you don't know, the hex value for like 0xFFFFFF, wait, is this number, but if we represent it in binary, you get this huge, these huge bytes, which in a 32-bit number, which contains 32 bits, this bit means a negative sign, right? So it's a -1 because when you have a negative number, it's actually inverted. So every one in here is actually 0, if you want to think about it like that, which would and +1, of course. So that's because you don't have -0, right? So that means that this is actually -1 in a typical integer, which good on Java. That's fine. Good on Java for optimizing that, but it doesn't help our case. We don't want to do that. What we want to do is, if we quickly find our thing, is not return that integer, but instead return like -1. But this is actually enough, right? That's how many bytes? That's 3 bytes. That's more than a short, right? That should be more than a short, but less than the full like integer limit thing. So that should be, theoretically, if we just run the Java compiler on it, another instruction, unhandle tag 3. So that's interesting. Tag 3. A load. Maybe not. What were the tags again? Okay, I went away to my Java specification for the virtual machine, right? We want to go here and find the class file format and the tags, which is tag. What was it? We have a tag for that. So that's actually constant integer. So weird design, right? Java can push a byte, constant byte. Java can push a short, which is 2 bytes, but it can't push 4 bytes. That's okay. So I guess we're not doing sum like that. We're doing it with a smaller size. So maybe let's actually do int 16, and that being a 16 value. Why not? So that should mean we can push just a short, and that should be more than enough. I mean, we haven't really reached that. A short is more than enough in our case, but yep. So now we need to find the instruction again for pushing a short. So that's 6.0 instruction. The short push, right? Short push. Short push is just 2 bytes, and its opcode is 0x11. Right, that's what we wanted. So let's open up our editor, right? So nvim on the javaslib, nvim qt on javaslib /source/mainrs. we're gonna go into jlib source. Right, so not main arrest, but we wanted to check out the code itself. Still running, so my other editor had it open for some reason. Let's quit. Wait, quit. Quit. Let's first quit. Yep, we open it up, so that's essentially public, right? And now we have a new opcode, so that's gonna be constant opcode for push, and that's push for the short, and that's essentially, as you saw here, 0x11. 0x11. Let's actually keep it away from these guys. Let's have it somewhere around here. Push. So I feel like push is just where is it? Can be just very quickly implemented, right? So that's gonna be, if we go to the serialization, we want to have essentially we want to do deserialization, right? Probably, and also to have push. So push is just a value of a 16-bit integer. A 16-bit integer. That's it. So, I mean, it would complain itself, right? But let's actually go to serialization for the instruction. Right, and let's do self, and it's gonna be push. So that push actually has a value, and the way you serialize that is just bytes extend. Essentially, bytes extend. Come on, extend value for the other one, and bytes extend opcode for the push to be bytes, right? It doesn't matter because it's the same thing, but still value, which I'm not sure that the value is actually the immediate byte and byte are sure the value is also in a big endian to be bytes. How did I know it's big endian, you might ask? Well, in here it says that it's made like this, which I think is big endian for what I remember. Again, don't quote me on that. We'll see. Well, I mean, it will either give us a correct number and we'll move on, or it will give us an incorrect number and we'll actually check it with just Python and like moving it around. So moving the bytes around. So then we also need deserialization. So deserialization is just check the opcode. Opcode push is essentially just self push, and we want to push the value. We want to get the value of 16 bytes, right? So I guess that's an read I64. Now we need to add even more stuff because this wouldn't compile. Okay, let's take this and just do the exact same thing, but with iret instead. So that's an I16 and an I16 and I16. All right, so that's 16 done. We have serialization and deserialization, so that should mean that now if you run the disassembler again on the stuff, we're missing comma. Okay, Rust. Deserialized 145. Deserialize 145. Come on. All right. And now we have an unhandled tag for 3. Alright, so yeah, that we checked, we know why. But at least now we have serialization and deserialization for side push, which should mean that if we quit this and instead open it up on hog source main.ls, we should be able to now do what? So for the integer 16, we can just do code block push. We want to do the instruction what? A side push with the value being value, right? That's simple as it is. And then block code push the code instruction iret, because we want to return an integer or not. Sret iret returns an integer. Ooh. Okay. The current method must be of type boolean. Oh, so it's any of them. Yeah, that works. That's basically it. Alright, so we've implemented that, and now what we should see is instead of output we should have the function return integer, right? Return integer. So essentially, though actually it's not that. I'm sorry, I just realized something. It's not that, it's actually S, I think, for short, although I'm not 100% sure the notation. So yeah, we still haven't gotten to the point where we can like fully take this and take this specifically, like the signature of functions and declarations and stuff. Signature, descriptors and signatures. Signature. Here. A signature attribute. No, we don't want a signature attribute. Do we have something that's capital I, space? I remember there being some table that had them all in a thing, but I'm not sure. So we had like a table. Yeah, here it is. So for short, it's S. Right, sign short. That's fine. So that should mean that if we compile this and run it, we should get the correct one, right? So we want to run hog, and that's it. So it's a value, but we have a weird value, I guess. Okay, a value equal to the dereference of value. We have just a reference to it. I mean, it's fine. And it's not an integer, it's an I64, so I16 instead. And that's it. And what do we get? Instruction to be byte, not implemented for iret. Okay. So we now need to change serialize. It's kind of annoying having to jump around this much, but it's what you get for doing this. So you want to do just self iret, and it's I remember it being just the same as the return instruction. Alright, that's it. And now if you successfully wrote the class, okay. So we have the class output. And if we go to out, we make a file like test.java, test.java, public class tests, public static void main string args, essentially just have system out println, and we are going to put this under a package called temp, and we're going to import temp.sum, temp.return integer dot output, I guess. Oh yeah, so the class is output, so you do then a short result equal to temp output, undo temp output return integer, and that should mean that if we print the result, it should be 69, we hope, at least. So now we quit this, we JavaC with test Java, class output package temp. That's weird, very much so. Maybe we can actually, well, I mean, okay, we can make a directory called temp and move both test Java and output class to temp and cd into temp. Right, so Java C test Java. Weird. Cannot find symbol output. Package temp. Right, so when we were doing this, did this have anything about packages? It did. Okay. Okay. So, alright. Okay, so maybe, yeah, right, so we need to do a little bit of more stuff than just that. Let's actually try to disassemble that one we did in here, where we had temp, cargo run dash bin j disassembler on similar class. We panicked at opcode of 0x8. I think I can fix this. Sum.java and b, we can just return an integer like this. Maybe we can just do something like this instead. 8, because we have that done. And I need to also change hello Java to we can comment this out. For maybe not in this result equal to sum out println, and that's our result, right? So that should be it for what I can imagine. Let's actually move some class and remove hello class. Alright, Java C dash D here, hello class Java and some Java. Alright, that should have updated them. Again, we go into temp, and now we want to disassemble them. They should have everything correct for what I can imagine. Right, if we do Java hello dot Java temp hello, Java temp hello could not overload the main class temp, or maybe it's here, Java temp hello. It returns 8. Sure, I just wanted to validate that it's true. And now we want to run the disassembler on temp slash sum class opcode 10, which the opcode 10 needs what? Oh, it's the thing again. Okay, let's change the signature once again. I'm sorry, I'm just very much tired with this Java BS. Right, so sum and you are also sum, and you're just a short. Makes sense. So now we can compile it yet again, like this, and run the disassembler. Come on. Disassembler on terminal class. Another opcode 0x10. I'm not sure what you want from me. Okay, 0x10 is byte push. Sure. I can parse that. That's fine. But what if I don't want to parse that and I'm just too lazy to do that right now? Let's actually return a value like 800, which should be way more than enough to satisfy the optimizations that Java does. So that's temp, and we get this. So we have sum.java. We have a class named temp/sum. Sure. Okay. The source file is sum.java. Okay. The temp/sum. This class is temp/sum. Superclass is Java lang object. That much is figured, right? So what do we have in here? We have essentially what? We have the sum function, but the class itself is actually temp/sum. I mean, sure. I mean, we can change that in code in here. So it's, instead of doing output, it's, well, why am I here? Okay. So instead of output, the string output, we want to do temp/output because it makes sense. All right, go back and yet again run hog. Right, so here we go as soon as we're able to run hog. Right, so here it is. Right, so we wrote the output, and the output is here. Move output class into temp. So you want to check move the last one and move it into here. So now we should be able to run Java. Let's see into temp Java C on test Java, but you have that in your class. I'm not sure what you want from me, right? So we have cannot find symbol temp.output. Okay, we have that. Can I do output class? I mean, sure, test Java. It's in the same directory. Not sure what you want from me. The class names output are not only accepted if annotation processing is explicitly requested. Okay, temp output. All right, output class. It's a public static. This class is also public static. Let's actually do access public. Not sure if that helps our case, but it's fine. Okay. Cargo run hog, go into output, go into temp, and copy output class from the last one into here. Can I do dash and D here. Test.java. Okay. Cannot find symbol. So you have two errors. One is the fact that import temp.output cannot be found. But we do that. The class is temp/output. Right, we do this. And from what I know, that's all you really need. Right, because the disassembly for the Java disassembler, like for the sum, temp/sum, is it this? Yes, so it's sum.java sci-push. The access flags for the function are 101, which is fine, right? We have temp/sum, that's the file. This class is temp/sum, and if we disassemble our output, actually, because we didn't do that, output.class, temp output.class. What do we have? This class is temp/output. I don't see anything that might say otherwise, that this can't be used. I mean, we can try to do something like using class files, using other languages with Java, the code in Java in another language, but more like don't know with other programming languages. Anyone got any? Can I just see something with other languages? Can I? C#, Java and C#, using C# from Java, calling C# code from Java. You should use the Java native interface if you want to call your into DLL. And Wikipedia, Java native interface, JNI. I don't want to do JNI. Calling C# from Java, like JNet. CLI solution quickly for that on existing code which is already exist. Use .NET native, so along with H files, jextract tool to generate Java interfaces from the C header. No. Okay. Right. Class files and linking with Java bytecode. A glance into the class. Can I class file bytecode? Does class be include the bytecode Java P? Why do you need to use to see the Java bytecode? You can simply go to the Java class containing the Java bytecode executed by the Java virtual machine, etc., etc., etc. Okay, let's roll back a little bit. So we want to go into temp, right? Not temp. We want to go into the output, right? We want to go into temp. Can I move test.java to the previous directory? Because I remember that explicitly that something like this worked with test.java. It worked somehow, right? It worked somehow. Okay. All right. Java temp.test. Written integer operand stack overflow. Right. So that's something that you need to check. So that's fine. So that's my problem. The problem we had in here is the fact that we don't specify the max stack, right? The max stack that ever gets is 1, and we have 0 locals. 0 locals, right? This should be handled, by the way, by the assembly itself. That's fine, right? That's not too bad. Cargo run dash dash bin, and that's hog. Stack Overflow, yes. Okay, we generated that output. Go into the output, and we can move the output class into temp, and then just recompile. Dash D here with test.java. Alright, and let's now just run the Java the project. So that should be temp test. And we get 69, right? So that's really cool, right? We have the actual thing working. So we have 69. What more can we do? Well, we can even do something like now if we want to do sum today, we probably have to also have expressions. So let me think a little bit. So expressions, right? An expression tree, or an AST, as you've heard sometimes, is the structure of the entire expression. So a tree that represents your expression. What does that mean? I went into it a little bit in the start, but that's essentially when you have something like a plus b times c, right? A plus b times c. That would then be turned into AST by most languages, where you have a plus sign on the left side. You have a, right? On the right side, you have another instruction. That's multiply, right? Why? Because, well, this has a higher priority. This gets analyzed first, so that's why we have this. So we want to first find the result of this expression, right expression, and the AST looks something like this. So we want to add the left side, which the left side is just a, with the right side, which is a multiplication of b and c. Right. This gets generated automatically by the actual compiler behind your languages, right? So now we need to actually represent that in some sort of way. So the way we're going to represent that is, now we have that value, right? We have that value. We should also represent an AST, right? An expression where we have an operand, remember this, plus or times. We have an operand, OP. We have a left side of the tree, which is either a value or another AST. As we remember from here, it's either a value or another AST. We can then do something like an AST value, which is either a value or an AST, which is just a box to an AST. Left side is going to be an AST value, and right side is going to be another AST value. Okay, that's our AST. But we also need to define the operator. So the operators we're going to have right now is just plus. Of course, operators have priority, you have parsing the expression, a lot of stuff that we're not going to get into today. I mean, it's already been like an hour and 40 minutes, so probably not getting into it right now. But now, instead of returning just the value, we can just return an AST, right? Or I guess an AST value. So an AST value is either gonna be the AST, which is a tree, or just the value. That's what we want. So let's actually do that. Let's actually refactor our code. So now, instead of this, we're gonna have an AST value, which is gonna be this, like so. Alright. And in here, we now need to also match that return type. Since now we're not matching just the integers themselves, we're also matching the actual operators and the actual AST values. So first of all, we start with the AST value. Is it a value? Well, okay, it's a value. That just means that we do the same exact stuff we did before. Can I? Okay, and then we're going to match v yet again, match the value that we get, and if the value is an integer, we're going to return an integer. Okay, what if it's not an integer, right? It's a tree to go, and then it's a tree. So we have AST. We should now match the AST operand. That operand, of course, we know is just a plus. And if it's a plus, then we just get the left side and the right side, and we have to evaluate them and just sum them up. So that's when the design choices kind of branch out in different ways. So currently AST has, like, we have to do a lot of stuff to get these results. So maybe AST value should actually have something else. So AST value should actually be AST value should have something like AST value, and we should have a function like evaluate to evaluate the value. Right? So it should take in some sort of block, which is a code block, as a mutable reference, and it should kind of load its instructions onto the stack. And what it should do is actually push the value of this onto the operator stack. Right. So what do? Well, we're going to have to match ourselves, and if we're a value, self value, we're going to do v eval. I guess eval is a little bit of a weird thing. Maybe push might be a little bit more correct, because we're pushing into the stack. Let's keep it evaluate. Let's keep it simple. We can always factor that later. So we want to push block. Right. We want to take in the value and just evaluate it. Okay. And if it's a tree, what do we do? Well, same thing. AST, just AST evaluate. Alright, and what does AST do in this case? Well, AST should have a function also called evaluate, so should value, right? So AST evaluate can take itself and also the mutable code block, so that we're able to push our code. So we can now do match self operand, and if it's self plus, we should evaluate the left side, evaluate the right side, and then call iret on it. Right now we're sure that we only really have integers. Later on we're going to have to kind of change this. So value is going to be a structure, and then we're going to have value type, right? We're going to have types for integers, for floats, for doubles, whatever, right? You can, but that's for later, right? Right now we know it's integers, so we're sure we can just do something like a block called push code instruction I-add, right? I-add, I think I-add is just one instruction. I don't think it's anything else. Then we can take in self and evaluate the left side of our block. We can take in the right side and evaluate it as well. So that means that on the stack, right, we have an integer on the stack. Here we have another integer being pushed onto the stack, and then with this We're taking the two integers on top and we're popping them, and we're just adding them together and giving them back to the stack. Right. So that means that at the end of this we should have just an integer, right? And now what we just have left is this, right? So what would happen? Imagine the following situation. We're evaluating a plus b. We would go into the operator, we would go into the left side, then we're going to jump back over to here, where we'll check if it's a value. Is it a value? It's a, so it's a value, so we just load that by doing f and evaluate self commutable code block. We like to do, right? This we have to do. And then we evaluate, we push that onto the stack, then we check b, evaluate b, see it's a value, then jump into here, evaluate that, that's on the stack, I add them. That's how simple it is, right? Then we can do self, can match self, and if it's case self int 16 value, we can just do sci push, right? So block code push code instruction and sci push with that value. And also I feel like value is a reference, so that's just gonna be value. That's fine. Okay, we have this. So now with our expression, let's actually do something more complicated, right? So what are we gonna do? We're no longer doing that, we're going to do AST. So we're gonna prepare the AST. Let's actually have like an AST. Actually here is box new of AST. So essentially in here the AST is gonna have the operator equal to op plus. The left side is going to be the AST value of, let's actually do something like 34 plus 35. Right, let's actually do a value 34, and then the right side is gonna be a alright, so that's a value in 16, right? And the right side is gonna be similar, except it's gonna be 35. Right? So that's the AST, and that's the entire thing. And now we need to evaluate that AST. So in here, instead of doing all of this crazy stuff, we can simply take this code for returning and go ahead and do, alright, v evaluate with our mutable block, code block, and on the stack we know we're expecting an integer, right, any integer, and we're just returning that. So that should mean that this, after it's done, should just be, if it works of course, 34 plus 35, which should output 69, right? So let's do this, I guess. Hog. Close the limiter, closing the limiter. Alright, way too few closing pairs. Alright, now let's run it. So plus, we have a random L at 151. Yep, this is a comma. Not a comma, but a semicolon. And an OP plus. OP plus. Where do we check that? Did they do OP add? No, associated item is not from AST. Yeah, that's self. It didn't crash. Plus, that's just OP plus. OP plus. Alright, compile, instruction to bytes, and that's IAD. Okay, so we still need to implement IAD, and that's fine. That's source Javers. Hello, Javers lib. And we're doing serialization, so that should be just serialize.rs. Serialize, come on. Javers lib. Student do what? Javers lib. Source. Into, okay, serialize.rs. Edit anyway. The other editor should update. So here we have IAD. I guess push. Here we should just do self IAD. IAD, which should just be, okay, so doing bytes extend opcode IAD to the bytes. Right, that's IAD. Right quit. Gotta go run. Okay, we wrote to output. Let's move the output class into temp. Update our test.java with the current package. And let's run it. So that's java temp.test. We did push, operand stack overflow. Yes, so that's a bit annoying. We should do where was it? Here, so we have 2 instead of 1. This should be handled automatically by the compiler, but that's probably gonna be done off camera. We're gonna do this off camera, and if you guys are interested, we're gonna probably even do it in the next episode, but that's only if you guys want to see that. So let's move that to temp and recompile and run temp test. 69, right? So let's actually change it, because before it was also 69. Let's do something like what? Like 210 and 210, which should equal to 420. It's very funny. Let's run it. Output, move the output into temp, recompile, and rerun java temp tests. 420, right? Cool. So we've got generation of this stuff working. We still don't have a fully complete, like we don't have the lexer or the parser for that matter, but we can now parse really basic stuff, right? I feel like now the next thing we should do before ending the episode is just putting everything together into what I like to call a build. A build is essentially, or a module, you can call it whatever you want. A build is essentially everything in your code, right? You take your code and then you parse it. That parsing should result in a build, which a build in our case is just going to be a set of functions, right? Build, and that's going to be functions, vector functions. So now instead of doing this, we should define a build. All right, define a build. Build equal to build with functions equal to a new vector, and maybe not even a vector, because right, let's actually do a hash map. Usually you would use a hash map, right? Usually you do hash map, and that's what we're gonna end up doing, is taking string, and this, we have a hash map of the name of the function to the function itself. So then we can just do something like build, which is a new hash map, and then just do for function in build funcs later. Great. We can do this. And now we can probably do this outside, right? We just, instead of doing this, we do func body iterate over all of the instructions, set the max stack to 2 and the max locals. They're currently very built-in, but we're going to fix that later. I'm going to create a new attribute for the code, and instead of doing the create method with this built-in name, we want to do fname and just do fname, right, with that name. And that should mean that now if we have like a return integer function, we should be able to do build func insert return integer to string and into an integer. That should hopefully now mean we should be generating, if maybe we have to include some collections for hash map. That's fine. Like this. I also make let build, we should make it mutable. And we wrote the output class, go to output, move output class to temp, and essentially recompile this here test Java and run. We get 420, right? And we can actually have even more functions, right? We can have even more functions, like for example, retInt2. Why not? Let's just do that quickly. Build func insert retInt2 to string int2, and retInt2 is just gonna be retInt2, essentially gonna be equal to a function with a body of vector instruction return return AST value 69, and that's going to be return integer 2. That should just mean that we should have like a return integer 2 that now, if we first compile with hog, okay, that's of course value int 16. We should have output the class, and if we change the test Java, probably get something like short results 2 is equal to temp output return integer 2. We should get system out println result, result 2 being result. And if we move output class to temp and we recompile Java and just run temp test, we should get 420 and 420. Huh? That's weird. Right. We have a bug somewhere. A big bug. Okay. Let's see. Why is it? Oh, maybe I do. Yeah, I probably. And that's just coding here. So that's result 2. We should print result 2. Yeah, just recompile Java and run it. Drum roll, please. 420 and 69. Alright. So we managed to do that, which is epic. Right, we did. We ended up, let's actually recap a little bit of the video. We started off by first generating hello world. We analyzed some of the packages to figure out how to actually link Java with our programs. We generated some test programs. Then we ended up abstracting away from those just test programs and having ideas of things like functions and instructions. We have ASTs, which are going to help us in the future. We've designed a basic API for evaluating ASTs. And we are now generating functions all on wheel by storing them in a hash map inside of a build. So I think we accomplished quite a bit today. Off camera, I'm probably going to clean some of the code up, probably add a little bit more functionality, like for example for integers, and probably work from there, right? We've accomplished quite a bit, and in the next episode, we're probably going to start by building a lexer and a parser. So that's gonna be fun. But for now, that's gonna be it for me. Bye.